Hey folks, I'm just going to go through the second law problems that I was going to do in class today. The worksheet's on the stream if you want to look at it while we do it. And I will post this video again for those of you who can't access Zoom. The goal here is to teach you how to apply Newton's second law to these situations. And the first problem is about a billiard ball. And so I'm just going to record some of the information that we get. And all of these problems require Newton's second law. When you see a problem that specifically mentions net force, you generally have less to do in the problem. And so this billiard ball is being hit and it's being accelerated because it's at rest and it's given a speed of 12 meters per second over a very small time interval. The question is, what is the net force? So to kind of think my way through this problem, the second law is net force equals mass times acceleration. So to get the net force, I need the mass and the acceleration. And these three pieces of data are the things that I need to get the acceleration. So I can write out this equation and say, okay, it gets 12 meters per second, starting at 0, and it takes 4.0 times 10 to the negative third seconds. So I divide that out, and I get an acceleration of 3,000 meters per second squared, which sounds astronomical, but it happens over a small time, and it's a billiard ball. And so all I need to do now is do net force equals mass times acceleration. That is going to be the 0.53 kilograms times my 3,000 meters per second squared. And so the net force in this situation is 1590 newtons, which is a much bigger number than we talked about in class previously, but still that's not that big considering what's happening. So that's problem number one. Problem number two. I watched a lot of like Disney things as a kid, and DuckTales was one of them. And so Huey, Dewey, and Louie are pushing on a bobsled. And so for this one, you get a lot of information about forces, and you're asked what the acceleration is. So sled. This is the first problem with the sled. And so for this one, it's going to make sense to sketch out a free body diagram. And it doesn't tell you really like which specific direction they're pushing in, so you can feel free to make things up. But for this one, Huey, Dewey, and Louie are each pushing with a force of 43.5 newtons. So you can just write out the values of the forces as opposed to like identifying the names of them. This would all be applied forces. And then Uncle Scrooge there is pushing against them at 90.3 newtons. So that would be the free body diagram. You could add in like a normal force and a force of gravity, but chances are good that we won't need them. We have the mass of the bobsled, and we want to know what the acceleration is. So we can just directly apply Newton's second law here. Now, the net force in this situation is something that I have to calculate. There are three separate 43.5 Newton forces. So for my net force, I'm going to do 3 times 43.5 newtons minus 90.3 newtons, and that's going to be the net force. That equals mass times acceleration, 127 kilograms times acceleration. So I would multiply this, subtract 90.3, divide that by 127, and I would get an acceleration of 0.317 meters per second squared. So that's the second problem. Third problem, we're back with the sled again. Where is it? Hang on, let me just get it. There we go. Okay, so Huey is on his own now. And I guess I'm not going to fit that in, so I'm going to cover this up in a second. But anyway, Huey is now on his own with the sled. That's sled part 2. And this time, the sled is being pulled at an angle, and there's no other there's no other like people pushing, and it says it's a smooth ice surface, and that basically means there's no friction. So probably a good idea to draw a free body diagram. And we can put the following forces in there. So normal force, gravity force. Huey's pulling the sled. Maybe we imagine that there's like a rope that Huey is pulling on, and that rope is at an angle. So this is kind of more typical of the problems I'm going to ask you to do, where you're like drawing a free body diagram and then analyzing it from there. The question is, if the sled starts at rest, how fast is it going after being pulled for that many seconds? And so the idea behind this one is we're going to apply Newton's second law first. Because I did draw a free body diagram, I'm going to focus on the x direction because I know that the sled's going to be accelerating in this direction. I'm going to apply Newton's second law first, get the acceleration, and then do kinematics to figure out its velocity after 1.15 seconds. In the x direction, there is just one force, and it is the horizontal component of Huey's force. So that tension force is at an angle, and so the horizontal component of that will be the tension times the cosine of the angle. And that's going to equal mass times acceleration. So you can do your trig first if you want to. You have to do it at some point in time, but I just like to write out the whole thing. So the tension force, it says, is 6.20 newtons, and the angle is 35 degrees. The mass of the sled is 4.60 kilograms. I guess I changed the mass of the sled drastically. Maybe it's just one of those plastic ones. And then the acceleration is my unknown. And so 6.20 cosine 35 divided by 4.60 kilograms. And I get an acceleration of 1.10 meters per second squared. To finish the question, I want to know how fast it's going after a certain amount of time. And so based on the conditions of the sled that I recognized, I know that I can use this equation because it starts at rest. And so I just do 1.10 meters per second squared times 1.15 seconds, and I get 1.27 meters per second squared. So that's 3 problems I went through pretty quickly. So kind of the general process here is you would want to start most problems with a free body diagram. Set up your Newton's second law equation and solve it for something. And if you're asked to do kinematics, it might be at the beginning so that you get an acceleration, or it might be at the end using the acceleration to solve a problem. And that's it.